So the first thing we're going to talk about is something called slope fields. Now, we're in differential equations. The ideal thing we want to do in differential equations is to say, hey, I can take my differential equation, y prime equals f of xy, and maybe I even have an initial condition, and I can solve. I can tell you explicitly, hey, this is the function. Now, that's the ideal. But oftentimes, we're not going to achieve the ideal. There are some very hard problems out there. Now, that doesn't mean we give up. You say, well, look, maybe we can still understand something about the solution. We can, as it says here, we can capture some of the behavior. And sort of the starting point here, so we're talking about the slope fields, is to say, well, what do we know? So we might say, look, I want to pass through the point A, B, which is another way of saying that y of A equals B. All right, that's a point. But we know one other thing. What else do we know about our function? So we have the differential equation y prime equals f of xy. We have our initial point, and we have one more piece of information. What do we have?
How y prime depends on the value of x and y.
Okay, so we have that. So in particular, what do we get? What? We get a slope. So we're told y prime equals our function f of xy. And so we say, look, I can plug in that point AB, and I get the value of y prime at that point. And we know y prime has meaning. Now, we can say, oh, well, it means the rate of change. How does the output change with the input? But it also has this nice geometrical interpretation, which says, oh, it's the slope of the tangent line. So really what we can say is, we may not have the solution, but if it passes through this point, we know what the tangent line looks like. And the tangent line is a pretty decent approximation to the curve. So it's like, oh, I can make little tiny pieces of what the curve looks like. And now what we do is we say, well, let's just take that idea and do it over and over and over again. So we're going to take a lot of points in the plane, and at every single point, we draw a small line segment. And what that small line segment corresponds with is what is the slope of that tangent line? And what does that tangent line look like of the curve that's a solution that passes through that point? So we're getting a good snapshot of local behavior, but we're getting it sort of collectively throughout the plane. Say, all right, great. And now, once we have that information, we can start doing some connect the dots type action, where we say, all right, I know locally how I behave, so I can move a little bit further. And now I can see how it's behaving in sort of the nearby place, change my behavior of what I think the curve should do, and keep going over and over. So we'll do some examples of what we mean by that and see, here's the idea, the philosophy. All right, so again, a slope field is essentially just a way to say what's going on with what the solutions look like. And we can use it to get some approximate solutions. Now, this really is an approximate solution. We're not explicitly solving here. What we're doing is we're saying, what is the behavior like? And so we can get some idea of what's going on. So there's good and bad news. The good news is any differential equation in the form y prime equals f of xy, we can carry this out. So we can capture the local behavior of any differential equation in some sense. The bad news is that the way we do this is we draw lots of line segments. And to get a really good approximation, we'll have to draw a lot of line segments. So that's computationally intensive. On the other hand, we have computers. And it turns out that computers like to compute. So they love drawing these things. Computers love making these kinds of visual images here. So what an age to be alive, that we have computers to help us. another thing to be aware of is because we are doing these approximations, sometimes if we're a little bit off, that little bit off can actually snowball the further on we go. And we'll see an example of this relatively soon. All right. So let's do one example. It says, all right, draw a slope field for the differential equation y prime equals x plus y. And it says, all right, well, where? You know, and the thing is, where do we draw the tangent lines? And we're going to do it on the integer points. So what we've drawn here is the grid. And in particular, we've gone from -3 to +3 in both the x and y direction. So everywhere where we see a crossing, we're going to draw one little tangent line. All right. Now it looks like there's going to be a lot. The good news is it's less than 50 lines that we have to draw. Do you see how many lines we have to draw? Less than 50, yeah. But how many? 49. See, I told you it's less than 50. Good. I keep my promises. All right. Now it looks like you're thinking, well, that's going to be the rest of class to do this. I hope not. But you'll get the idea. Hey, it takes a while to do this. Let's start at the origin. So what can we say? We're looking for these tangent lines. We have this differential equation y prime equals x plus y. What would y prime be at the origin? 0. So that means at the origin we would expect a flat tangent line. So we draw a small line segment that looks like that. So that indicates that at the origin we expect we're flat. 1 down, 48 to go. Well, we can speed things up a little bit because x plus y is actually pretty nice. So everywhere where x plus y equals 0, we're going to have the same slope. Where are some other places where x plus y equals 0? All right, someone suggested -1, +1. Okay. Anywhere else? -2, +2. Anywhere else? -3, +3. For what?
Other direction.
Other direction. Yeah, so +1, -1, +2, -2, +3, -3. And in fact, if you think about the diagonals, once we know what happens on a diagonal, it's going to be the same slope because it's x plus y is going to be constant on those diagonals. So really, we can save ourselves a lot of work. All right, move over to the right. X equals 1, y equals 0. What's my slope? 1. So we're going to draw a line segment with a slope of 1. And we're just going to use the fact that along the diagonals, it's always the same slope. All right. 2, 0. What's our slope? 2. So we come in and we draw a slope 2. And we're going to do that along that diagonal. Okay, how about there? 3, 0. What's our slope? 3. Okay, so it's slightly steeper. All right, now we have to come over 3, 1. What's our slope now? 4. Oh, we keep getting more and more steep. Now we don't want to make these too long. These are short line segments because part of the idea is the tangent line is approximation to the curve, but only nearby. So don't draw too long. So it's not like we're going to draw this and be like, whoa. No, just locally. We're capturing local behavior. Okay, 3, 2, slope is 5. And here at 3, 3, slope is 6. All right, well, we're more than halfway. We're doing great. How about over here? X equals -1, y equals 0. What's our slope? -1. So we draw a slope with -1 and we do it all along the diagonal. Great. Okay, -2 comma 0. Our slope is -2. All right, so we draw a slope -2. All right, so a little bit more down. And okay, at -3, 0, slope is -3. And here, -3, -1, slope is -4. I will say, in some sense it's hard to tell when you have steep slopes that they look very different. So it's at best an approximation. All right, so we filled in. All right, so there we go. There's the slope field. So not the most exciting procedure, but what do we learn? Well, we can start to see some behavior. For instance, we say, look, if we're over here, what's happening to our solution as we move from left to right? It's going to move up. What's happening, say, if we're down here? What's happening to our solutions? It's going to be moving down. So you can even just pick a point to start at. Now, if I start here, you can say, look, what's the tangent line telling us? Well, right now it says locally we should look something like this. So we say, okay, follow that along. As we move over, what's happening to our tangent lines? They're becoming steeper. And so we should be turning up. So as the tangent lines get steeper, we should be turning uphill. What's happening as we go this way to our tangent lines? Well, we seem to level off, and then it seems to go towards that. So based off of our slope field, we say, okay, this looks like it could be a potential solution, an approximate one. All right. Anything else jump out at you?
If it falls on that line with the slope of -1, it will never come off that.
Yeah, boy, there seems to be this nice solution right here. Can we check that? What is this line? Sorry, what?
X plus y equals -1.
X plus y equals -1. Okay, good. And we could also write this as y equals, if we move the x across, minus x minus 1. So it's the slope of -1, and the intercept is at -1. Well, okay, so the slope field seems to say, hey, that's a solution. Let's check. Well, quickly, what's y prime? -1. Good. What is x plus y? -1. So yeah, that's a valid solution. So we found one. Of course, we were lucky in that it was a line. If we were just below the line, starting over here, what would happen to us? We would go down. And notice that as we pull down, we're going to get more and more pulling down because our slopes are getting steeper the further away we get from that line. So we might start close to that line, but eventually we'd pull down. All right. So that's an example of how we draw a slope field and then how we can read off a slope field. Now you might say, well, great. But of course, that's a rough approximation because we're kind of sampling far apart, only 1 unit apart. What if we wanted to get a better estimate? How do we improve our estimate? What can we do?
Use a computer.
Use a computer. Okay. Yes? More samples. Okay. Yeah. So here's the same slope field. Each time, it's always y prime equals x plus y. I used a computer here. This is not hand-drawn. But you can see that, okay, of course, when we get here, everything's so small, it's almost like, whoa, there's too much information. So there's a trade-off. But we see, yeah, it really is capturing that behavior of we have that line, and then we can see that we have this nice turning up action going on above the line and a turning down below the line. And so one last thing here is that here's that slopeville. And these are not just approximate solutions, these are actually exact solutions. And you can say, okay, how did we do? Well, in some sense, I have to say I've done this problem before, so I kind of knew the answer. But you look and you say, that's not so bad. We were able to capture some relatively precise behavior of what's going on, all things considered, given how much we put into it. Now, two things to note. First thing to note is look at these solutions here. What do you see about the solutions at this point? They're pretty close to each other. How about over here? They're not close. So this is what we mean when we say even just a small change can lead to a very significant outcome that's different. So that's why we always take, approximations with a grain of salt. Approximations are almost always better the less we have to go. So the nearer we can stay, the better our approximation usually will be. On a side note, we did say we have one solution, which is minus x minus 1. In case you're wondering, can we solve this differential equation? And the answer is yes. So if you take minus x minus 1 plus some constant e to the x, those are all the solutions to this differential equation. So what you're really seeing here is that you have the line, then you have some exponential function that's coming off. And that's why you have this crazy behavior. We will be able to solve this. Not today, not tomorrow, but soon. And for the rest of our semester, we'll be able to solve that. Soon being a couple weeks. All right. One other thing, there's this nice little pro tip down here. So we're pros, so we should listen to and see what this says. And what does it say? It says, suppose you have a nice differential equation. Then different solutions cannot cross. Now what is that referring to? Well, it says that if you have differential solutions, we want to avoid this, where there's one solution that does this, and then there's some other solution, and I'll change colors here just to emphasize the fact it's another that does that. So when we have these kinds of nice, and again, what does nice mean? When we plot these curves here, we should never have anything crossing. So if something crosses, errors were made. But what is nice? So, a challenge. Do you know what nice means? Yes?
In that example where they cross, right where they cross, there's one solution, and the slope at that crossing point is different than the other one. So a nice differential equation is one where the slope at each different point is a constant.
Yeah, there's something highly suspect here. Now, of course, this is really kind of exaggerated. You can imagine, though, that we have something where we have this, and then maybe we can have something coming in like that, where that's two different solutions. And then here, of course, they're the same tangent line. So, do you remember what nice means?
No holes, no jumps, no asymptotes.
Okay, so you're getting back into what we were talking about last time, which says there's some notion of continuity. So nice is referring to this. So this is nice if we are continuous, and that's the no holes, no jumps, no asymptotes. And if partial f, partial y is continuous. So that's the second part that makes it nice. So those are the two things that make something nice. Now, if we're nice, why can't we have this? We should just state it out loud. Why can't we have solutions crossing if we're nice?
One line you have to jump.
But how do we know that? What does nice give us? If it helps, we talked about it last time. What did we talk about last time? Okay, all right. I know we can do this. All right. If you don't know the answer, give me a letter. E. Good choice. C. Bad choice. What? B? V. Well, both of those are bad choices, so it doesn't really matter which one.
Wait, don't we want it to be unique?
What?
Unique?
Yeah, it's unique. Wow, that's pretty good. Once you ruled out the A, it was obvious. Okay, good. Unique. Unique. That's the key word. See, nice implies unique. That's really what we mean by nice. Now, what is happening here? Why is that bad? It's not unique. We have two solutions passing through that point. So that's why solution curves can't cross if we have a nice differential equation. Nice differential equations say all our solutions are unique. We can't have two solutions go through the same point. All right, good. I'm glad you cracked the code. All right, excellent. All right, how do we use slope fields? Well, we use it to approximate. So we can say, all right, suppose we have the slope field. So here's the slope field for the differential equation. Y prime equals sine y minus cosine x. And you're probably thinking, this is a really bad lecture to try to draw what's on the board in real time. Should have printed it out ahead of time. But, okay, that's all right. What do we want to do here? Well, we want to graph some approximate solutions. And so that can give us an idea of what's going on. We can also do something like the following. Suppose we say y of negative 2 equals positive 2. Estimate y of positive 2. So in other words, we're saying, hey, we want a particular solution. The point that passes through the point negative 2, 2. Now you can't see it on the screen very well. There actually is a grid. And so negative 2, 2 is right here. There's the point negative 2, positive 2. All right, so let's just plot what's happening. So the way we do this is we just say locally what's the behavior and let the curve tell us what to do. So for instance, locally, this is our tangent lines. Now what's happening to our tangent lines as we move from left to right? Look at the slopes. What's going on? They're getting flatter. So that says, we're going uphill, but we're starting to sort of level off. Okay, so we're coming uphill, leveling off. What's going to continue happening next? It looks like we level off, we go down a little bit. Do we go down much? No, because notice we're going to start leveling off pretty soon, and the slopes are very shallow. Okay, and then what happens? Then we start to climb back up. And we go. Now we can go in the opposite direction here. And say, okay, here slopes are negative. They're getting a little bit more steep, but then they start to shallow out. So we're going to start going downhill, but then we are going to start to shallow out. So that's one approximate solution. Now, how do we use this to estimate y of 2? We say, okay, here's 2. And we come over here and say, well, it looks like that's roughly where we're hitting. And we come over here and we eyeball. So this is at 1, 2, 3. So it says, well, it's like 2 3/4 maybe. See, that's the nice thing about an estimate. You don't have to be exact. You have to estimate. And who's to say your estimate is better than my estimate? Well, I guess I get to say that on an exam, but all right. But we're just getting some approximations. So that's a way we can use it. Let's try another point. Okay, suppose we're down here. All right. negative 1, a negative 1. Okay, what's happening to our curve as we go from left to right? We're going down, and then what? Kind of level off, and then go up again. But not too long, and then we level off. See, because these directions tell us how steep we are, and as we go, it's telling us, are we becoming more steep, less steep? And so we can capture a reasonable approximation to our curve. And of course, we can go in the other direction as well. All right. So, let me ask you a question. Suppose we started over here. Do we have any sense of where we'll end up over on this left-hand side?
It should probably be in between the two that we already drew.
Yes, somebody has cracked our code. We should mind the gap. All right. Why? Well, look. What do we see about sine y minus cosine x? It's nice. It's continuous. You can take a derivative, no problems. So that says, look, whatever this curve does, what can't it do? It can't cross these two. So these two are pretty close, but it can't cross, and so it's going to have to shoot the gap. Well, does it? Of course we can make it, but, if we follow it along, okay, it goes down, levels off, comes up, somewhat levels off, starts coming down again, and seems to be pretty reasonable. So there we go. All right, and we can do another one. Same philosophy, same idea, just a different differential equation. Y prime equals x squared minus y. Again, you pick a starting point and you follow it along. Not a lot of thought has to go into it once you have it. You just have to say, okay, follow the behavior. So, what's our behavior? What are we doing? Down, and then leveling off, then going up. And I will say, for this particular differential equation, we will be able to solve this. Whereas this one is kind of hopeless. It's hard to tell, what's going to happen here? Yeah, we're going to do a turnaround and then whoa, they're going pretty steep. So, wow, this is great. We can do stuff. All right. Well, that's all I have to say about slope fields. Any questions before we move on to our second topic? All right. So, our second topic. Good. We're going to talk about separable differential equations. Now, I'm not defining what a separable differential equation is, but I am going to tell you how to solve it. But let's define it. Now, we should think about words. Words mean things. Look at this word, separable. What word does that remind you of? Separate. And that's the key to saying what's going on. So this is really something about a differential equation where you can separate something. Now the question is, well, what's being separated? So a differential equation is said to be separable if you can write it in the following form. Y prime, which another way to write it is dy dx, is a function of x times a function of y. So somehow we can pull them apart so they multiply. Now that's not really the separating part, but that's the kind of form we need. Now, why do we say we can separate? Well, the idea is to say, I want to separate the variables. Because we have two variables. There's y and x. X is our input variable, y is our output variable. And we say, look, one of our two sides, we're going to put all the x's, say, over on the left-hand side. And we're going to put all of the y's, sorry, our x's are on the right-hand side, y's are on the left-hand side. So the idea of separation is that we can separate the variables. Okay, so step one in how you solve it, I like to call this step the separate step. All right, good. Now there's two notations. The more rigorous notation is to say y prime over g of y equals f of x. The not so rigorous notation, but we will forgive you because we do the same thing anyways, is to say, another way to think of y prime is dy over dx. And so here's where it gets kind of makes a mathematician squirm a little bit, like, oh, you're not supposed to do that, but we'll let you do it anyways. When you look at dy over dx, there's a tendency to say, oh, there's something called dy, and there's this other thing called dx. And we sort of have them dividing one into the other. That's what it looks like. But here's why that's not what's going on. Dy over dx is a notation for one thing. It's not two things put together. But we will forgive you for this because it works a lot better if you just follow and break that notation. So think if we treat dy and dx as separate, then we say, oh, this is really the same as dy over g of y, f of x dx. So the key thing is we can break the two sides, separate them from each other. All right, separate. Pretty straightforward. The next step, step 2, integrate. Which is, we're solving a differential equation, which means really we somehow want to get rid of a derivative, and the way we get rid of a derivative is we integrate. And we're integrating both sides. So one idea says, hey, if I have two functions which are equal, what's true about their integrals? They're also equal up to, up to a constant. So if two functions match and you take their integrals almost match up to some constant. So that's why you need a plus c. Now you might say, I thought every integral had its own plus c. Why don't we put a plus c on the left and a plus something else on the right, maybe plus d? Why do we only need the one constant? Why not two? This is sort of the Hobbit type question. We've had first constant, yes, but what about second constant? Okay, someone has said, you can just subtract the one constant over. All right, that's actually a good idea. So there's a nice little philosophy here. So here's our constant philosophy, and which means our philosophy about constants. Not that this is our only philosophy and we will not change this. So our constant philosophy says that constants are like sponges. What does that mean? Well, that means that constants can absorb other constants. So for instance, suppose I take 2 times a constant. What do I have? It's a constant. And so I can suck the 2 into that constant and say, oh, I'll just treat it as some other constant. Maybe I'll use a different symbol. Maybe I'll be lazy and use the same symbol. What if I have e to a constant? What is that? It's just another constant. So I can oftentimes absorb constants into constants. And you'll see that we do this when we go through our simplification. So if there were 2 constants, one on each side, if we subtracted one over, I have a constant minus a constant, which becomes what? A constant. I can absorb the constants together. So we only need the one. All right. So first step was separate. Second step was integrate. Third step, well, I like to call it a silly name, uncomplicate. Now you might say, that sounds complicated. But I kind of wanted to have that theme going, 888. Separate, integrate, uncomplicate. So what do we mean by uncomplicate? Well, we've gotten rid of the derivative. That's the big challenge. But now we may say, well, we've got to solve for our y, and we might have an initial condition we need to solve for our c. Now, there's a question. When do you solve for c? And the answer is whenever it's convenient. So you could first solve for y and then solve for c, whatever that form it might take. Or you can say, hey, I'll solve for c right away because I see that I can do it very quickly. And then I'll solve for y. So it's up to you. So that's the philosophy. Separate, integrate, uncomplicate. And if you can remember that, you'll be able to solve our separable differential equations. All right. Do you have sort of an idea of the game plan? Yeah. All right. Good. Now, the practice. Examples. We have a cheat sheet here, should we get stuck. Find the general solution for x squared plus 1 tangent y prime equals x. So the first thing we should look at when we look at a problem is say, what technique should we use? What technique do you think we should use here? Yeah, separable differential equations, right? And you're probably thinking, how do we know that? And the answer is, it's over here, Steve. It says it. But suppose you were on an exam. We're not going to tell you this problem uses this technique, this problem uses that technique. So we want to get to the point where we're comfortable saying, aha, I can look at this problem and I can see that this problem is a problem where I should use the idea of separable differential equations. So looking at this, mentally, what are we checking for when we're saying, is something a separable differential equation? What do we check for?
We need to find a function of x and a function of y that we can multiply.
Okay, function x, function y.
There's, like, in the current example, there's a 3x squared, and then there's an e to the negative y, and you can separate those into an f of x and a g of y without doing any terrible math.
Right. So, I mean, if you can do this, really, yeah. So for me, I just look at step one and ask the question, can I succeed in step one? Can we separate? In any way, shape, or form. If I can't even do step one, forget it, hopeless. But usually the idea of the separation is pretty quick to see. So for here, what would I have to do to separate? Yeah, it's like, the only place where I see x's and y's mingling is over here on the left. Divided by x squared plus 1, they're no longer mingling. Life is good. Life is wonderful. All right. So this is a problem that does involve separation. Tangent y prime equals x over x squared plus 1. We've separated. Now, I would probably prefer to write this as tangent y dy is equal to x over x squared plus 1 dx. All right. Success. We have a problem that is separable. We have been able to separate. What do? We integrate. All right. We have two sides. I'll make you a deal. I'll integrate one of these two. You have to integrate the other. Which one do you want to integrate? Okay, so you guys picked the hard one. Good. Fantastic. I appreciate that. I appreciate you giving me the easy one. All right. So how does one integrate x over x squared plus 1 dx? Yeah, we use substitution. You can almost see it mentally. So once you see enough integrals, you start to like spot things. And basically one of the things you should learn is like, oh, I don't recognize this right away. And you quickly think, let me try a couple substitutions in my head. What's the substitution that you're seeing? Yeah, x squared plus 1. So if we let u equal x squared plus 1, what does du equal? 2x dx. And at this point, we're like, we were so close. We have the x, we have the dx, but we don't have the 2. Is all hope lost? Some people said yes. No, I would not exaggerate that much if all hope was lost. So the thing is that these constant values are easy to move around. So in this case, move that around. So half du is x dx. Okay, great. So what did we get? The right-hand side, we get the integral. There's a 1/2, there's a du, and that takes care of the x dx. So the x dx became 1/2 du. This x squared plus 1 downstairs becomes what? 1 over u. What's the integral of 1 over u? ln u. So 1/2 ln of u plus the c. But what's u? X squared plus 1. All right. Good. So that was the right-hand side. The left-hand side is a freebie. Doesn't require any work. This is on the list of 10 integrals that you need to know. And you're probably thinking, there's a list? There should be. A list inside your hearts. You know, there's 10 functions you should know the antiderivative for. And if you're not sure what they are, you should contact me and I'll tell you. All right, so the integral of tangent y is log secant. So since it's on my list, I just pull it off my list. So there we go. Log secant is 1/2 log x squared plus 1 plus c. What do we do now? Well, we want to uncomplicate. How can we uncomplicate things? In particular, how do we get rid of the logs? E to the log secant becomes secant. Okay. Now this side, well, it might take us a little time to digest. What can we do with this 1/2 in front of the log? Yeah, so the constants in front of logs come in as exponents. So we can write this side as e to the log of the x squared plus 1 to the 1/2, which is really square root of x squared plus 1. Now, another question I have is, see that plus? Because there's e to something plus something. What does plus in the exponent become sort of when we separate? It becomes times, right? E to c. Because like if you have this, you'd add the exponents. So if you had things being added, you would multiply. So e to the log of square root of x squared plus 1 is what? Square root of x squared plus 1. What do we do with this e to a constant? Yeah, it becomes a constant. So we'll be lazy and use the same constant. Okay, and now I would say this is okay. I'm happy stopping here with this problem. We're not going to stop. We still have time. Someone might object and say, Steve, there's still a secant. I want to free my y. I want it to taste sweet air, freedom. Can't we just like do the thing? And I'm like, yeah, I know what you're talking about. I know you want to do the thing. Can we? What's the thing? Arc secant, inverse secant. Just like log has this inverse function of e, secant has an inverse function as well. It's the inverse secant called arc secant. So you might say, hey, shouldn't our answer be arc secant of some constant c, square root of x squared plus 1? And I'll tell you, if you left that, I would probably still give you credit. But there's kind of sort of, it gets messy with the details. This is actually better capturing the behavior than that. And because we don't have a lot of time, I'm going to sort of wave my hands. You can see I'm waving my hands right now as I speak. What's happening is that what can come out of the arc secant function? Well, it's an angle between 0 and pi. So the only things that can come out of arc secant are between 0 and pi. But y doesn't have that restriction. Y could be outside of the range between 0 and pi. So if C said like, you know, y was 100, that doesn't get captured here. But it does get captured there. So there are subtleties. There are subtleties. All right. I'm sorry. It's probably too early in the semester for subtleties. We'll save that for the end of the semester. Okay. All right. Now let's just go for it. Let's just see if we can get both these in the next couple minutes. I think we can do it. All right. We're going to find y of x, given that y prime equals 3x squared e to the minus y and y of 2 equals 0. Okay. What's our technique? Yeah. They're going to hear that a lot, especially on our next class. Okay, so we have, this is like dy dx equals 3x squared e to the minus y. So when we separate, what does this become? E to the y dy equals 3x squared dx. Because when you multiply the e to the minus y across, you might say, well, I'm dividing by e to the minus y. Dividing by e to the minus y is the same as multiplying by e to the y. That's the separation. Now, we do the integration. Integral of e to the y? E to the y. Oh, nice. Integral of 3x squared? X cubed. Plus the c. Now, we have to solve for the constant here, because we're finding a particular solution. We have an initial value. Last problem, we didn't have an initial value. We were looking for a general solution. Do you want to solve for the constant now or later? Let's do it. Let's go for it. Now, what does this say? The constant says when x equals 2, y should be equal 0. All right. So we have e to the 0 equals 2 to the 3 plus c. What does that tell us about c? -7, right? E to the 0 is 1. 2 cubed is 8. So we update. So now we plug in our value for c, and we say, okay, our update says e to the y equals x cubed minus 7. How do we get that y out of that exponential function? Natural log. So y equals natural log of x cubed minus 7. Done. Done. Okay, that one wasn't so bad, so we have time for one more. Let's go for it. We can do it. We can do it. Okay, y prime equals x over 2y plus 4 and y of square root of 7, okay, equals 0. All right, good. We can do this. All right, first step. Separate. It's not separated yet, right, because there's x's and y's commingling here. We don't want them to commingle. Okay. So we separate. What do we get if we separate? 2y plus 4 dy equals x dx. Okay, what's next? Integrate. Great. Integral of 2y plus 4. Y squared plus 4y. Integral of x. Half x squared and plus c. What comes next? Use our condition. Okay, so when x equals square root of 7, y equals 0. Well, the good thing is y equals 0 is very nice. We get 0 equals square root of 7 squared, 7 over 2 plus c. So what is c? -7/2. Great. We're doing fantastic. Y squared plus 4y equals 1/2 x squared minus 7/2. Now, what do we want?
Perfect square.
Someone said, we want a perfect square. When do we want it? Now. Okay, all right. What are we really after? Well, we're after 1y. How many y's do we have? 2. That's one too many. So we somehow want to condense that. And someone said, hey, if we could make this into a perfect square, we can rewrite it in such a way that there's just one y. Now, what would I have to do to make this a perfect square? Add 4. In other words, we're completing the square. And we're saying to that 4, you complete me. You had me at hello. You had me at hello. Now, can I just add 4 arbitrarily here? No. But if I do it somewhere else so it balances, then I'm okay. All right. So what do we have? Y squared plus 4y plus 4 becomes y plus 2 squared. All right, equals a half. Then we have x squared minus 7 halves plus 4 is plus a half. So I can write this as 1 half times x squared plus 1. And see, here's the great thing. We had 2 y's before. Now we're down to 1. 1 y to bring them all. 1 y to find them. Right? 1 y to... Well, anyways. All right. It's been a while. We need to finish up. We're already over time, but we only need about 30 seconds to finish up. We just need to get that y by itself. How do we do it? Okay, good. So what does y plus 2 equal? Square root of this other side. But then someone said plus or minus. So y is negative 2 plus or minus. Now, there's a problem with this. What's wrong with our answer? There's 2 answers. How many answers should we have? 1 answer. Okay, so we have 1 too many. So we must choose. Do we choose the plus or do we choose the minus? And why do we choose the plus? Okay. Which one are we going to choose? Good. You cracked that code. Why? We still have to satisfy that initial condition. Negative 2 minus something will never get to 0, but negative 2 plus something can. So, aha, that initial condition comes back. Double whammy, helps us get the answer. Done. All right. To be continued next time. Have a good day.